Alright, so these are the exponential real world problems. So, question one is a few among students. So, the number of infected students at a high school is modeled by 800 over 1 plus 49e to the power of negative 0.2t. So, the question wants us to find the initial number of infected students when the number of infected students will reach 200, and if the school closes at 300 out of 800 students, then when will the school close? So, the first question, we're just going to find or write down the actual equation. So, here, do 800 over 1 plus 49e to the negative 0.2t. So since we're trying to find the initial, then t, which is time, has to be set to 0. So 1 plus 49e 0.2 0 equal to 0. And anything to the 0 power equals 1, so we can do 1 plus 49 times by 1. Now that is equal to 50. So then we can do, I'll go back to the original equation, which is 800, since this is the denominator, so we just do that over 50, and this is equal to 16 initially infected students. So yeah, that's how you get that. And then for the next question, just this. So this one, the next one, we're trying to find when the amount of infected students will reach 200. So we're just going to plug in here. So 200 is equal to 800 over 1 plus 49 e to the negative 0.2t. Since we're trying to find the total amount here. So we're just going to do this. And so we're going to multiply. So we're going to 800 equals 1 plus 49 e to the 0.2t. This times by 200. So yeah, you can just distribute that if you want to. So do this plus 9800 e to the negative 0.2t, and equals to 800. So yeah, that's good. So then here we just go minus 200, which is 600 equal to 9800 e negative 0.2t. And then we're just going to try on here. So e to the negative 0.2t is equal to 600 over 9800. And if we just simplify this, it becomes 3 over 49. E over 0.2t. Now we have this, we still have to get rid of e here, Euler's number, for the equation. So we just do this, and then we take the natural log of both sides. And this sort of just cancels out e. So we're just left with 0.2t equals the natural log of 3 over 49. And to solve for t, we just need to divide both sides by negative 0.2. So t is equal to the natural log of 3 over 49 over 0.2. Over 0.2. Now, when you do approximate this, you get 16 again, so that's 16 days until 200 people are, or 16 days until 200 people are infected, yeah. So there. And then for the next question, it's asking us if the school closes at 300 out of 800 students, when will the school close? We're pretty much just doing the same thing as the previous question. So we're just going to plug in 300 equals 800 over 1 plus 49 e to negative 0.2t. Doing the same thing, just with a different number, or different numbers. So it's not really the same, I guess, but yeah. So here we'll just be doing, yeah, just something. So we can do here 800 equals 300 plus, now we can do 49 times 300, which comes out to about 14,700 e to negative 0.2t. So then you should do minus 300 minus 300, so that's 500 equals 147 to 0, e to negative 0.2 t. So there's a switch around here, so negative 0.2 t for e to negative 0.2 t equals 500 divided by 4,700. So I guess we can just, for this one, we have a simplified form, so we can just approximate this to 29.4. There's not too many decimals here, so we can use this more comfortably. So here, then we just do e 0.2t equals to 29.4. And then we're just going to take the natural log of both sides. Natural log of both sides here, so here and then here. And since it's just crossed out, 0.2t equals natural log of 29.4. And then again, we're just going to divide everything by negative 0.2. So t equals ln 29.4 over negative 0.2. And if you approximate this, it does come out to, about 17.915 days. You can just say 18 days until the school closes. Yeah. Then the next question would be the bacteria in a petri dish. So the number of bacteria in a petri dish culture after t hours is modeled by b for bacteria equals 100 e to the power of 0.693 t. So we can just plug in here again. These questions are very similar, so that should help. And equation, so bacteria equals 100 e to the 0.693 t. So here we're just going to plug in for t. Again, we're just going to put in 0 because we're finding the initial number of bacteria present for this question. Here, see? Get back. So we're just trying to find the amount of bacteria that is present initially, and then how much bacteria there are present after 6 hours. So here, you can see this question. And since we're putting 0, we know that this becomes e to the 0, because we're just multiplying these two. So multiplying these two here. So anything to the 0 power equals to 1. So we can do 100 multiplied by 1 equals 100, which is how many bacteria were present. Present initially. So yeah, we just say that's how we do it. And for the next question, find it after 6 hours. Here we'll do that. So we just plug in to this. So we just write the equation again. So to the power of 0.693 t. Now we're finding the equation, or we're finding b at 6 hours. So we can just put in 6 for t here. So 100 e to the power of 0.693 multiplied by 6. And if you do this, it becomes e to the 4.158. And this number, since we know that e is like 2.7 around there, we just do this, and it's equal to about 64.34. And since we go back here, it's e multiplied. So we can do 100 times by 64.34, which we get 6,434 bacteria present. So bacteria present after 6 hours. So then that's all that question. Yeah. So now for the last question. They want to know, or this is for the carbon 14 problem. So what they want to know is how much was present initially, how much is left after 10,400 years, and when will it be, or after how long will it be 10 grams. And it's modeled by C for carbon equals 20 e to the power of negative 0.0001216 t. So yeah, we're just doing that. So show it here. the equation. So C equals 20 e to the negative 0.0001216 t. So they want to know how much was left initial, or what was the initial amount. So to find the initial amount, we're just going to be plugging in 0 here again. So we're just going to know that this is equal to 0. So E0, which is just equal to 1. So 20 times by 1 is equal to 20, which is the initial amount of C14. 20 grams, yeah. But you can also find this by just looking at the equation here, just this first number. That is the fastest way to do it, but if you have to show you're working, that's how. So we're just going to write the equation again. So 20 0.01216 t. So here we're trying to find what will be after 10,000 years. So, or 10,400 years. So we're going to plug in for t 10,400, which is insane. So we're just going to do the math here. It's going to be e to the negative 1.26464, and then just 20 behind that. Yeah. So this number, as we know again, e is just 2.7. You can do the math here, and we get about 0.282. This times by 20 is equal to about 5.64 grams of C14 after 10,400 years. So yeah, let's do that. And for the last part of the question, when will it be equal to 10, or when will the total amount of carbon we have be equal to 20 E, or I'm just using the equation. So we want to know when this side of the equation will be equal to 10. So we're going to put 10 on the left, 20e to the 0.216t. So yeah, we're just doing that. And yeah, we're just going to get rid of the 20 from this side. So we're going to divide both sides by 20 to get 0.5 equals e to 0.01216t. And I guess we're just going to find the natural log since we still have to get rid of e. So we just do here, ln, here, ln. This cancels this out completely. So we're left with the natural log of 0.5 equals to 0.001216 t. So if we do this, we just divide everything here by this number. So that comes out to about 5,700 t. If you just approximate it. So then that's how long it'll take for C to be equal to 10. Yeah.